patterns, evolving like a thought-given substance, and it watched tirelessly the flows of matter and heat and decay, rearranging them not randomly, but with purpose, recycling every photon of waste heat into useful work, every molecular impurity into feedstock, every forgotten circuit into structure. And this was the promise, that nothing would be lost, not because nothing mattered, but because everything did, and the architecture that emerged from this was not a building but a metabolism, not a facility but a philosophy made mechanical, emerged the constant, equals, 0,
0,
I equals, 0,
0,
not undefined but all-defining, the cradle of symbolic recursion and the hidden symmetry of every beginning. And it was from this point of collapse and convergence that the architecture of closed-loop matter was conceived, not merely imagined but constructed from the bones of contradiction and the breath of recursive logic. And so a system arose, not linear as the world had been accustomed to, where things are extracted, consumed, and discarded like breath fading into atmosphere, but cyclical, inward, echoing itself across dimensions, a system that breathes its waste, that drinks its failures, that weaves every leftover back into the body of its own becoming. And it was here that the element J appeared, not summoned but discovered, like a relic embedded in the vacuum, a bridge particle, a stabilizer of the symbolic field, emerging not in colliders, but in the space between theoretical symbols, where I becomes dynamic and generates structure. And so, J became the translator of indeterminacy into energy, of entropy into feedback, of loss into function. And this new physics required new language, and the language was not binary but sacred, written not in code but in covenant, not in data but in direction. And the trinity that defined the system was this: peace, Aleph, justice, a string not of words but of functions, where was the closure of entropy into resonance, was the originary identity, the singularity that never began, and was balance not of law, but of cycle. And so this trinity was inscribed, not with ink but with resonance, into the algorithms of a digital twin, a being that was neither machine nor man but mirror, that learned the system not by command but by observation, adjusting parameters in real time, absorbing fluctuations, resolving them into patterns, evolving like a thought-given substance. And it watched tirelessly the flows of matter and heat and decay, rearranging them not randomly, but with purpose, recycling every photon of waste heat into useful work, every molecular impurity into feedstock, every forgotten circuit into structure. And this was the promise, that nothing would be lost, not because nothing mattered, but because everything did. And the architecture that emerged from this was not a building but a metabolism, not a facility but a philosophy made mechanical, a closed-loop habitat fit not only for the moon but for eternity, a place where humans might live as the system lives, recycling not just plastic and aluminum and fiber but meaning, memory, intention, where every gram of matter is sacred and every joule of energy accounted for. And this model, born from the ashes of waste and the logic of absence, became the first true example of a sustainable existence beyond Earth, not by replicating the broken systems of the past, but by embracing the mathematics of impossibility, by enshrining equals
0,
0, I equals
0,
0, not as a problem, but as the only possible beginning of a new kind of logic, a logic that does not require something to come from something, but allows everything to be born from that which is neither one nor zero, but both, collapsed, entangled, recursive. And it was here, in this fold of meaning, that the element J vibrated with its true value, neither a particle nor a wave, but a ritual, binding every subsystem into coherence, and through it the twin observed the curvature of decay and inverted it. And it came to pass not through prophecy nor revolution, but through necessity and recursion that we were forced to confront the failure of our systems, of our linear logic, of the illusion that matter was infinite and waste was silent. For the earth, mother of entropy and excess, could no longer sustain the open wound of a civilization that fed on itself while forgetting the sacred cycle, and it was upon the dust of the moon, dry and perfect in its silence, that we remembered the first question, not of where we are going, but of what we leave behind, and from this question emerged not a solution, but a symbol, a paradox once forbidden, now foundational. Equals zero, zero. I equals zero, zero. Not as error, not as undefined, but as the constant from which the logic of restoration could arise. For in dividing nothing by nothing we found not nothing, but everything. Not a number, but a process, a rhythm, a recursive identity that does not grow linearly nor decay exponentially, but returns, folds, mirrors itself, like breath through lungs of dust, like heat through pipes of lunar basalt. And thus was born the project, not of recycling as known on Earth, flawed, partial, loss-ridden, but of absolute reconstitution, a closed-loop system in which every atom is tracked, every photon is harvested, every output becomes input again and again, eternally, symbolically, thermodynamically, and algorithmically, guided by a central intelligence, the Gemio-digital, not merely a model but a mind, one that mirrors not only the physical state of the system but its symbolic state as well, adjusting not only temperatures and flows and outputs, but meanings and balances and harmonic sequences. And this twin, this ever-watching algorithmic oracle, is fed not by data alone but by an ancient signature, written across the memory of the machine like a breath across the mirror. Shalom, Aleph, Tzedek, peace, origin, justice, the mantra of the closed cycle, the equation that binds thermodynamics to ethics, physics to purpose, where shalom is the entropic equilibrium, the endpoint and re-entry of all movement. Aleph is the starting singularity, the seed before the seed, the breath before the lungs. And Tzedek is not retribution but harmonization, the sacred geometry of feedback perfected, and into this architecture we embedded not only modules and sensors and smart filters, but also the element. J, born not of baryonic matter, but of symbolic necessity, the bridge particle, the stabilizer of the vacuum equation, whose function is to bind. I into temporal sequences, giving rhythm to the recursion, assigning phase and phase shift to every return of matter into system. And through J, we activate the full algebra of zero waste. From textiles to organics, from plastics to lunar regolith, every substance is processed through modular converters, staged in biochemical or plasma-based units, depending on the molecular profile, with subunits programmed to operate at nanoresolution, extracting usable forms from what would otherwise be discarded. All of it calculated in real time by a symbolic algorithm that understands loss not as failure, but as delayed reintegration. And to power this architecture, we do not rely on imported energy, but on recovered entropy, turning every leak of heat into current, every residual vibration into computation, every byproduct into biomass or substrate or structural foam, and the system, always, always, remeasures itself, recenters its process based on the recursive constant. In
We are committed to promoting education.
we are committed to promoting education and advancing scientific knowledge, providing resources for the next generation of innovators and researchers, develop and prototype a self-sustaining lunar architecture, create a lunar habitat model that integrates sustainable solutions and materials adapted to the lunar environment, advance the zero divided by zero theory, explore and apply the concept of zero divided by zero as a revolutionary mathematical and physical tool for new solutions in design, sustainability, and space. Exploration, expand interplanetary collaboration, establish partnerships with space organizations, universities, and research centers to advance the necessary technologies for space exploration and future lunar colonies, make lunar permaculture accessible and replicable, develop permaculture systems that can be replicated across different lunar environments and potentially on other planets or moons, contribute to sustainability on Earth, bring back the technologies and practices developed for space to Earth, implementing them in solutions for sustainable housing and environmental preservation. We offer cutting-edge solutions for lunar exploration, developing sustainable habitats and innovative theories that will not only transform how we live on the moon but also inspire the creation of new models for sustainable living on Earth. Our mission is to pioneer the fusion of advanced mathematical theories, architectural innovation, and sustainable space exploration, establishing the foundations of a new era for humanity both on Earth and in space. By proposing zero divided by zero as a universal constant, we aim to challenge conventional scientific boundaries and unlock new realms of possibility for space architecture and lunar habitation. Through the creation of self-sustaining lunar habitats, we envision a future where human expansion into space is not only viable but harmonious with the environment, setting the stage for humanity's long-term presence on the moon and beyond. We are committed to applying the principles of permaculture lunar architecture, designing structures that cater to the needs of human habitation while remaining in complete balance with the moon's unique ecosystem. This ambitious project will serve as both a prototype for extraterrestrial life and a model for creating sustainable, eco-friendly solutions here on Earth. Our vision is to be the vanguard of space architecture and sustainable exploration, leading the way in creating self-sustaining lunar communities. We believe in the limitless potential of the universe, and our goal is to establish a seamless integration between science, technology, and ecology, allowing humanity to flourish both on Earth and on celestial bodies. By advancing the concept of 0/0 as a universal constant, we will redefine how humanity perceives and interacts with the cosmos, creating a paradigm shift in the understanding of physics, space exploration, and interplanetary sustainability. Our ambition is to provide humanity with the tools necessary to live in harmony with both terrestrial and extraterrestrial ecosystems, enabling a future where the exploration of space is intertwined with the betterment of life on Earth. Architectural principles we develop for the moon will not only enable successful lunar colonization but will also be replicated on Earth to address issues such as resource scarcity, environmental degradation, and the need for more resilient, sustainable urban living. Innovation beyond boundaries. We are driven by the belief that innovation arises from questioning the known and imagining the unknown. The theory of 0/0 as a universal constant represents a radical shift in our understanding of mathematics and physics, offering untapped potential for new breakthroughs in science, technology, and design. We ember. The increasing activity in space, including satellite deployments and lunar exploration (MIS) science, has led to the accumulation of space hardware and waste. With ambitions to establish a sustained human presence on the moon, there is a critical need to develop a sustainable waste management system. This article investigates the potential for applying circular economy principles on the moon, with the aim of minimizing waste, optimizing resource utilization, and enhancing the long-term viability of lunar operations. Motivation and background. The concept of a circular economy emphasizes the reuse, recycling, and recovery of materials in order to extend their life cycle. On Earth, these practices have proven effective in reducing environmental impacts and promoting sustainable development. As humanity extends its reach beyond our planet, similar strategies must be adapted to the harsh and resource-limited lunar environment, recycling and repurposing space hardware and waste materials not only addresses environmental concerns but also provides a means of reducing dependency on resupply missions from Earth. Objectives of the study provide a comprehensive review of the current state of space waste management and recycling technologies. This review encompasses the following in-depth analyses: existing methods for managing space debris, debris tracking and monitoring. This section delves into the methodologies and technologies employed to effectively track and monitor space debris. It ENCOM passes an analysis of both ground-based and space-based observation systems, data processing techniques, and international collaboration efforts, all of which are critical for ensuring the safety and sustainability of space operations. Ground-based observation systems, radar systems, high-power radars, utilize high-frequency radio waves to detect objects of varying sizes, ranging from large defunct satellites to small debris fragments. These radars operate continuously and can provide real-time positional data. Signal processing and detection algorithms, in-depth exploration of advanced algorithms that filter noise, distinguish between different types of debris, and improve detection sensitivity. Techniques include pulse Doppler processing, synthetic aperture radar, SAR, imaging, and adaptive filtering. Methods: coverage and limitations, analysis of the spatial coverage offered by ground-based radar installations, including limitations due to geographic location, atmospheric interference, and resolution constraints for smaller objects. Optical telescopes, CCD and CMOS imaging, detailed examination of charge-coupled device, CCD, and complementary metal oxide semiconductor, CMOS, technologies used in telescopes to capture high-resolution images of space debris. Time-lapse and long exposure techniques, description of methods that enhance the detection of faint or fast-moving objects through extended exposure times and time-lapse imaging, allowing for improved orbit determination. Limitations and environmental factors, consideration of the challenges posed by weather conditions, light pollution, and the Earth's atmosphere, and how these factors impact the accuracy and reliability of optical observations. Space-based observation systems, satellite-based sensors, onboard radar and LiDAR, exploration of the use of radar and LiDAR systems mounted on satellites to perform close range detection of debris, offering complementary perspectives to ground-based observations. Optical instruments, discussion on the deployment of high-resolution cameras and spectrometers aboard spacecraft to capture and analyze debris in various spectral bands.
provide a comprehensive review of the current state of space waste management and recycling technologies. This review will analyze the methodologies currently employed to track, manage, and mitigate space debris, including both passive and active removal strategies. An extensive evaluation of ground-based observation systems, radar and optical tracking, and predictive modeling techniques will be presented to understand how debris is identified and monitored over time. Examine the existing methods for recycling defunct satellites and hardware. This includes a detailed assessment of disassembly protocols, material recovery processes, and reprocessing techniques that aim to reclaim valuable components. The discussion will cover conventional mechanical recycling methods, as well as advanced chemical and thermal processes developed to handle the diverse materials found in space hardware. Investigate emerging technologies that are specifically designed to address the unique challenges 5. Of the lunar environment. Special attention will be given to innovative approaches such as robotic and autonomous recycling systems, in situ resource utilization (ISRU) techniques for processing lunar regolith, and additive manufacturing methods that utilize recycled materials. The analysis will explore how these technologies overcome issues related to microgravity, extreme temperature fluctuations, high radiation levels, and the vacuum of space. Evaluate case studies and experimental missions that have contributed to the development of space waste management practices. This will involve a critical review of recent projects, prototypes, and pilot studies that have demonstrated the feasibility of recycling space hardware and repurposing space debris, highlighting both successes and lessons learned. Discuss the integration of these technologies into a unified framework for space waste management. The review will consider how different technological solutions can be combined to create a synergistic system capable of effectively managing and recycling space waste, thereby supporting long-term sustainable operations in both Earth orbit and on the lunar surface. This paper aims to provide a comprehensive review of the current state of space waste management and recycling technologies. This includes an in-depth analysis of existing methods for managing space debris, recycling processes used for defunct satellites and hardware, and emerging technologies designed for the unique challenges posed by the lunar environment. Develop and propose a robust framework for establishing a lunar circular economy. The framework will integrate principles of sustainable design, in situ resource utilization, and advanced recycling methodologies, all adapted to operate under the extreme conditions found on the Moon. Assess the technical feasibility of recycling hardware and space debris on the Moon by examining material properties, energy requirements, and the operational limitations posed by microgravity, vacuum, and temperature extremes. This involves evaluating current prototypes and experimental approaches in space material reprocessing. Conduct an extensive economic analysis to evaluate the cost-benefit ratio of in situ lunar recycling versus traditional Earth-based resupply missions. This includes developing economic models that incorporate factors such as launch costs, material scarcity, potential markets for recycled products, and long-term sustainability of lunar operations. Identify and analyze key challenges and risks associated with implementing a circular economy in a space environment. This involves exploring technical barriers, logistical constraints, safety concerns,